In this section, we are going to talk about planes that are tangent to a three-dimensional surface and about linear approximations. I want to motivate this discussion a little bit. We're going to start by thinking about the single variable case. All right, so I have here a parabola. One of the points through this parabola is the point 2, 1. Now, what happens when I zoom into this point? Okay, notice what the curve starts to look like. Before long, it doesn't look like a parabola anymore, does it? It looks like just a straight line. This is a property of all single variable differentiable functions. If a function is differentiable at a point, if you could take its derivative, if you zoom in close enough, it will look just like a straight line. Okay? Which means we can approximate the curve close to the point by the line tangent to the curve at the point. Right? So here's the tangent line. You could find this tangent line by finding a point on the line, right? Which of course would be the point that we're tangent to. And the slope of the tangent line, which of course we can find with the derivative, right? So with those two pieces of information, we can find the tangent line. And if I zoom in, before long, you can't tell the difference which is the tangent line and which is the curve. Okay? We want to have a similar sort of property in 3 dimensions. We want to have a similar sort of situation in 3 dimensions. So here I have a paraboloid, and I have the point 2, 1, 2 that is on the paraboloid. Notice what happens when I zoom into the point. If I zoom in close enough, before long, it looks like, instead of a paraboloid, it looks like it's just the plane, doesn't it? And so what we want to do here is we want to find a tangent plane to the point. That's going to be the goal of this section, to find a tangent plane at a given point. That tangent plane can approximate the surface when we're very near the point. If I zoom in now, before long, you can't really tell the difference between the surface and the plane. Okay? Now this has some practical applications that you may be familiar with. Every 3D modeling software that I know uses planes to approximate a curved surface. Okay, so this particular software I'm using, it's called Blender. It's a free modeling software. So I'm going to add a sphere in here. Now that doesn't look very sphere-like, does it? Okay, but notice that it's definitely made up of planes, right? Now what happens if I increase the number of planes? Okay, oh hey, now that's looking like more of a sphere, doesn't it? If I go a little bit more, okay, that's definitely looking like a sphere. And as I increase the number of planes, you could still see, by the way, you can see all those little triangles, right? It might help if I'm in wireframe mode, so it looks a little busy. This sphere, it's just made up of a bunch of triangles, and those triangles are just segments of planes. But as I increase the number of planes, I get a better and better approximation to a sphere, until you can barely tell that it's not really a sphere at all. It's just a bunch of planes. All those planes come together and they approximate the surface of a sphere. Okay, so that's one application of this. We can approximate a surface, a curved surface like a paraboloid, with just a bunch of planes. Why would we want to do that? The equation of a plane is much, much easier to work with than the equation of a paraboloid. The equation of a plane is a linear equation, in that we call such an equation like this a linear equation, in that the variables all have power 1 and they're all separate. They're not multiplying each other. just like the equation of a line would be in 2 dimensions. Okay, so we call it a linear equation not because the graph of the equation is a line, but because the equation itself has properties like the equation of a line in 2 dimensions. So linear equations like this are very easy to work with. We have a whole algebra dedicated to working with linear equations like this. It's called linear algebra. And we're very good at working very quickly with these kinds of equations. So we often like to approximate nasty surfaces, curved surfaces, with a plane. Okay, makes it much easier to work with. Okay, now I do want to caution you, just like in single variable calculus, you can't always find a line tangent to a point, right? For example, I have some funky looking function here. Notice in particular at the origin, doesn't matter how much I zoom into that point. I'll never zoom in close enough so that it will look like we have a straight line, right? Because it's a sharp point. The function, this particular function, is not differentiable at this point. Doesn't matter how much I zoom in, it's not going to look like a straight line. Similarly, in 3 dimensions, we sometimes have surfaces that are not differentiable at a point. They have a sharpness to them. Okay? So no matter how much I zoom into the origin here, zoom in forever and ever and ever, it's still nice and sharp. In fact, it doesn't look like I did anything, right? The surface looks exactly the same. Okay? That point stayed sharp. It doesn't look like I just have a plane now. It looks like the same surface as I had before, right? And I still have that sharp point. This point would not be differentiable. The way we define differentiability for these higher variable functions, for these surfaces in higher dimensions, is if you can approximate the surface with a plane at a point. If you can, then the surface is differentiable at that point. Okay? We call this property local linearity because the surface can be approximated by a linear function at the point. In the case of a function like this, a single variable function, we're actually approximating it with a line, right? We can approximate it very accurately with a line at the point. In the case of a smooth surface like a paraboloid, we're approximating it with a linear function, a linear surface, the plane. Okay, so we say that the surface is locally linear because we can approximate it with a linear equation. So how do we actually go about finding the equation of a plane tangent to a surface? Well, remember, we need 2 things to find the equation of a plane. We need a point in the plane, and we need a vector normal to the plane. Now, point in the plane, that's easy. We know we want our plane to be tangent to the surface at a point. The point at which we're tangent at, it has to be in the tangent plane. Otherwise, we wouldn't be tangent at that point, right? So we have what we need to find a point tangent, a point in the plane. How do we find a vector normal to the plane? So our strategy here is the strategy we often take for finding a vector normal to the plane. If we could find 2 different vectors that are parallel to the plane, that are in the plane, then we could take the cross product of those 2 vectors and find a vector normal to the plane. So how do we find those 2 vectors that are in the plane? Well, if they're going to be vectors that are in the plane, okay, if they're going to be vectors that are in the plane, then those 2 vectors, because the plane is going to be tangent to the surface, those 2 vectors will also be tangent to the surface. So if I can find two vectors that are tangent to the surface, then I'm good to go, right? Now, I already have a way to find information about tangent behavior to the surface, partial derivatives, right? So if I look along the trace where I hold x fixed, I can maybe use my partial derivatives to find information about the tangent behavior to the curve, to that trace at the point in the direction of y. Okay, and I could do the same thing with my other partial derivative. If I look at the trace in the x direction holding the y value fixed, I could take the partial derivative at the point, and using that partial derivative information, I can construct a vector tangent to the surface. And then using those two vectors, which are now tangent to the plane, okay, I can take their cross product and find a vector normal to the plane. So that's going to be our strategy. So let's see how this works in practice. Okay, so let's use the particular function we're dealing with in this example. Z equals 1/3 x squared plus 2y squared. Okay, so I'm going to take the partial derivative with respect to x. I get 2/3 x. And if I take the partial derivative of z with respect to y, I get 4/3 y. So these will tell me the tangent behavior of the traces going in the x direction, the tangent behavior of the trace going in the y direction. I'm interested in the tangent behavior at a particular point, though, right? I want to find the tangent plane to the surface at xy equals 2, 1. So if I plug in this x and y into my partial derivatives, I will find information that tells me the tangent behavior to the traces, okay, to the surface. So let's plug in the x and y values. In this case, there's only an x to plug into, right? So at this particular point, as the x is changing and I hold y fixed, the z changes, the change in z is 4/3. Similarly, if I plug in the point here, plug the 1 in, I also get 4/3. So it happens to be the same rate of change in both directions, right? Now, I know information about that tells me what's going on tangent to the surface in these two directions. Okay, I know the rate of change in these two directions. How do I translate this to a tangent vector, though? Well, to understand this, it's helpful to think about what this is telling us. Okay, so if I have, let's say, in this direction, okay, maybe my trace looks like this. Let's throw it in a. Okay, so this is my x-axis, this is my z-axis, this is the trace going through y equals 1. So I'm holding the y fixed, I'm looking at how z changes, okay? And I'm interested in the value when x is 2, something right there, okay? What this 4/3 is it is the slope of the tangent line to the trace at that point. Okay, now how do I take that and turn it into a vector? Well, think about what slope tells me. Okay, slope of this line is my partial derivative with respect to x at the point. I could think about that as my partial derivative over 1. And slope is how much my z is changing with respect to x. Okay, so this is saying for every 1 unit of change of x, this is how much my z changes along that line. Okay, in this case, that partial derivative is 4/3. Okay, so that means for every 1 unit of change in the x direction, I'm changing 4/3 units in the z direction. And if I put those together, I can get a vector out of that. Okay, for every 1 unit of change in the x direction, I'm changing 4/3 units in the z direction. And then since I'm holding y fixed, I'm not changing it all in the y direction. So this would be the vector tangent to the surface at the point in the x direction. Okay. Similarly, I can use this. This is the rate of change in the y direction. So for every 1 unit of change in the y direction, I'm increasing the z value of 4/3 in the z direction. Okay. And since I'm holding the x fixed at x equals 2, I'm not changing the x at all. So these are going to be my two tangent vectors. Okay, so generally, my tangent vectors can be found by looking at the rate of change in the x direction. For every 1 unit of change in the x direction, this is how much the z changes, okay, along that trace. And in the y direction, for every 1 unit of change in the y direction, this is how much the z changes. That's what my partial derivatives tell me, the rate of change of z per change of x, or per change of y, while holding the y fixed or the x fixed. Okay, so those are our tangent vectors generally. And so I can now take the cross product of those and find my normal vector. Okay, so my normal vector would be the cross of 1, 0, 4/3 with 0, 1, 4/3. So I get I, J, K, 1, 0, 4/3, 0, 1, 4/3. And I get, for my first component, 0 minus 4/3. For my second component, 4/3 minus 0, but then because it's the j, I add a negative in front of it. So I'll get negative 4/3 again. And for the k component, 1 minus 0. So there is a vector normal to the tangent plane. And since I already know the point at which I'm tangent at, I'm ready to go, right? Here's the xy. I also need the z, by the way. So if I plug in xy, the tangent point would be 2, 1. And then if I plug those in here, I can find the z value also. So if I plug 2 in, that's 4 plus 1 in for y. 2 times 1, that's 2. So 4 plus 2 is 6, divided by 3 is 2. The z value is 2. So this is the point at which I am finding the tangent plane. Okay, so I've got the point, I've got the normal vector. So the equation of the plane would be negative 4/3 x minus the x coordinate of the tangent point minus 4/3 y minus the y coordinate of the tangent point plus 1 times z minus the z coordinate of the tangent point equals 0. There is the equation of the plane that is normal to this surface. So let's take a look at another example. Here we want to find the equation of the plane tangent to the surface z equals 3 sine x plus 4 sine 2y minus sine 3x minus y at the point x comma y equals 0, 0. Okay, so we need two things to find the equation of the plane. We need a point in the plane, and we need a vector normal to the plane. Now, for the point in the plane, we know we know the tangent point will be in the tangent plane, right? And we know the x and y coordinates of that tangent point. But to find the equation of the plane, we also need the z coordinate. So let's start by just plugging in 0, 0 to find the z coordinate of this point. So let's find that tangent point. By plugging in x equals 0 and y equals 0 into this equation. So I get 3 sine of 0 plus 4 sine of 2 times 0 minus sine of 3 times 0 minus 0. Now, notice the interior of the sine function, what I'm plugging in, it's just going to be 0 in every single case, right? So I get sine of 0 here, I'll get sine of 0 here, I'll get sine of 0 here, and sine of 0 is just 0, right? So it doesn't matter what I'm multiplying, I get 0 plus 0 plus 0. Overall, I'm just getting 0. So the point I'm looking at is the point at the origin. The tangent point is the point xyz equals 0, 0, 0. Okay? Okay, so tangent point's done. Now we need the normal vector. Remember our strategy for this. To find a normal vector, we're going to get two vectors that are parallel to the plane and take their cross product. Now, if there are two vectors that are parallel to the plane, since the plane is tangent to the surface, that means the vectors are also tangent to the surface. I can find two tangent vectors by using my partial derivatives. That gives me information about behavior tangent to the surface, and then I can use those to construct vectors that are tangent to the plane. Okay, so I'm going to want some partial derivatives here. So let's take the partial derivative of my function with respect to x. Derivative of 3 sine x is 3 cosine x. Derivative of 4 times sine of 2y. Because we're treating y as a constant, all of that's just a constant. Derivative of a constant is 0. It'll just go away. And the derivative of negative sine 3x minus y, I'll need a little bit of a chain rule here. I get negative cosine 3x minus y. I left the insides the same, and then according to the chain rule, I need to multiply by the derivative of the inside when I'm done. Derivative of 3x minus y with respect to variable x is just going to be 3. Okay, so my partial derivative of z with respect to x is 3 cosine of x minus 3 cosine of 3x minus y. Okay? Let's take the partial derivative of z now with respect to y. Partial derivative of z with respect to y. Let me scroll up so we can see it. Since I'm taking the derivative with respect to y, I'm treating x as a constant, which means 3 sine of x is a constant, derivative is 0. Derivative of 4 sine of 2y is going to be 4 cosine of 2y times the derivative of the inside, which is just 2. And then the derivative of negative sine 3x minus y is going to be negative cosine 3x minus y times the derivative of the inside with respect to y, which is just negative 1. So this becomes 8 cosine of 2y plus cosine of 3x minus y. All right? So I can use my partial derivatives to tell me about the behavior tangent to the surface. But I'm interested in a particular point. So what we want to do is we want to plug in the x and y of the particular point we're interested in, the point we want to be tangent to. Okay, So let's start with this guy. The partial derivative at xy equals 0, 0. I'm going to get 3 times cosine of 0 minus 3 times cosine of 3 times 0 minus 0. Again, the interior of these are just going to be 0. So I get cosine of 0 and cosine of 0. Cosine of 0 is just 1. So I'm just going to get 3 here minus 3 here. I'm getting 0. Okay? So that means in the x direction, for every 1 unit change in x, I'm moving 0 units in the z direction. Okay? And of course, I'm holding y fixed, so I'm not moving in the y direction also. This is going to be one of our tangent vectors. All right? Now let's do this one. Let's plug in the particular point we're interested in, point 0, 0. Partial derivative of z with respect to y at 0, 0. So plug in, we get, so I'm plugging into this function here. 8 times cosine of 2 times 0 plus cosine of 3 times 0 minus 0. I'm going to get cosine of 0 and cosine of 0, so I get 8 plus 1, which is 9. Okay? Which means now I'm moving the y, so for every 1 unit change in the y direction, my z is changing 9 units. And I'm not changing at all in the x direction because I'm holding x fixed. Right? So these here, these are my tangent vectors. There are 2 vectors that are parallel to the plane, so if I take their cross product, I will get a vector normal to the plane. So my vector normal to the plane is going to be 1, 0, 0 cross 0, 1, 9. 1, 0, 0, 0, 1, 9. If I take this cross product, I get for the first component 0. For the second component, 9, but it'll be the j component, so it's negative 9. And for the last component, 1. So that's my normal vector. I now have a vector normal to the plane. I have a point in the plane. I'm ready to construct the equation of the plane. Okay. Remember my tangent point was 0, 0, 0. And so I get 0 times x minus 0 minus 9 times y minus 0 plus 1 times z minus 0 equals 0. Plugging in the components of my normal vector and the x, y, and z components of the point in the plane. Right? Now, of course, this can be simplified. This is just 0. And then anytime I subtract 0, I could just say y instead of y minus 0. So if I simplify this, I get negative 9y plus z equals 0. Okay, that is the plane tangent to the surface. Let's take a look at what that looks like. Okay, this is the surface we're dealing with. It's kind of cut off in its current orientation, so let me zoom out a little bit. Pretty weird looking surface, right? Those sine functions mean a lot of repeating, and because there's multiple of them, it's weird. Okay, it's like these repeating mountains. Now we want to be tangent at the origin. Change the color on that. Okay, that's the point at which we're tangent to. Let me zoom into it so we can get a better view. And the tangent plane we found was the plane, what was it? Negative 9y plus z. Negative 9y plus z equals 0. Okay, so you could see it kind of doesn't look tangent if you look at it right here, right? But if you look at it down this way, you could see that it will indeed be tangent to the surface. Okay, and the more we zoom in on the point, the more the surface and the plane look the same. In fact, it looks so much the same, you get this interesting effect where the software can't decide whether it wants to display the plane or the surface. Let's do one more example. This example is a little bit different. The surface we have here, we cannot express it as z being a function of x and y. Notice the x, y, and z variables are all mixed together on this side of the equation. All right. We still want to find the equation for the plane tangent to this surface. We want it at the point -1, -1, -1. So the process is essentially the same. We just have to be a little bit careful taking the derivative of the equation of this surface. Okay. So if we want a tangent plane, we need a point. The tangent point, we don't have to calculate it this time. It's given to us. -1, -1, -1. That's the point we're going to be tangent to. That's going to be a point in the plane. Now let's find the normal vector. We're going to do this the same way. We need the partial derivative of z with respect to x, partial derivative of z with respect to y. This time, z isn't on just one side of this equation. So what we're going to need is we're going to need to do implicit differentiation. So to do implicit differentiation, I'm going to take my equation, x squared plus 10xyz plus y squared plus 8z squared equals 0. And I'm going to differentiate both sides with respect to one of the variables. In this case is x. And I'll need to do implicit differentiation. So I'll take the derivative with respect to x. That means I'm treating x as the variable, and I'm going to treat y as a constant. Z, I am going to treat z as a function of x. Okay, so we'll see what this looks like as we work through it. So if I take the partial derivative with respect to x, derivative of x squared is 2x. For 10xyz, x, I'm taking the derivative. Y I'm treating as a constant. Z is a function of x. So this is actually going to be a product rule. Okay? So I'm going to start by taking my constants, the 10 and the y, and I'll just leave them out here. They just come along for the ride. And then in here, I'm going to do my product rule. Product rule for x times z. Okay? So derivative of x with respect to x is 1 times z unchanged. Plus, now I leave the x unchanged, and now I'll take the derivative of z with respect to x. Now, we're treating z as a function of x. So the derivative of z with respect to x is the derivative of z with respect to x. That's what I'm looking for, right? That's what I want to find, the partial derivative of z with respect to x. So I shouldn't be surprised when I get that. Okay. Plus derivative of y squared with respect to x, y is a constant, so that's just 0. And then the derivative of 8z squared. Here I'm going to need a chain rule. I'm taking the derivative of z with respect to x. Z is not my variable of differentiation, which is why I need a chain rule. So I'm first going to do a power rule. So 8z squared, if I do the power rule there, I get 16z. And then because z wasn't my variable of differentiation, I need to multiply by its derivative. So I'm going to multiply by the derivative of z with respect to x. Okay? And then, of course, on the right-hand side, derivative of 0 is 0. So the derivative part is done. Now what we want to do is we want to isolate the partial derivative of z with respect to x on one side of the equation. Okay? So let's distribute this. To start off with, I get 10yz plus 10xy partial z partial x plus 16z partial x. Now what I like to do is I like to get all of my terms with partial z partial x in them on one side of the equation by themselves. So I could either move both of these to the right-hand side of the equation, or I could move everything that doesn't have that partial z partial x in it to the right-hand side of the equation, leaving these on the left-hand side. I think that's what I'll do. So I'll move these to the right-hand side of the equation. That leaves me with 10xy partial z partial x plus 16z partial x on the left-hand side of the equation. On the right-hand side, I have negative 2x minus 10yz. Okay. The reason why we did this is because now everything on this side has a partial z partial x in it, so I could factor out that common partial z partial x. So if I factor out the common partial z partial x, leaves me with 10xy plus 16z. The right-hand side doesn't change. And now if I want to get partial z partial x by itself, all I have to do is divide by this. So partial z partial x is going to be the negative 2x minus 10yz stays in the numerator. And then I divide by this, so I get 10xy plus 16z in the denominator. Okay, so that tells me for this surface how the z changes in the x direction. Now what I want to do is I want to find how it changes at the particular point, negative 1, negative 1, negative 1. Okay? So I'm going to plug in xyz equals negative 1, negative 1, negative 1. I get negative 2 times negative 1 minus 10 times negative 1 times negative 1 divided by 10 times negative 1 times negative 1 plus 16 times negative 1. Lots of negative 1s. Okay, I'm going to get positive 2. Let's see, this should be a parenthesis. Negative 10, positive 10, and negative 16. So 2 minus 10 is negative 8. 10 minus 16 is negative 6. And so I get 4/3. Now this was how much z changes in the x direction, which means for every 1 unit of change in the x direction, my z is changing 4/3 along that tangent vector, along that tangent line. And I'm holding y fixed, so the y is not changing at all. So I've got one of my tangent vectors. Okay? We just need to do it all again for the y. So now I'm going to take that same equation, x squared plus 10 xyz plus y squared plus 8z squared equals 0, and I'm going to take the partial derivative of both sides with respect to y. Okay? Now I'm going to be treating x as a constant. I'm differentiating with respect to variable y. And z, I'm going to treat as a function of y. So whenever I take the derivative of z, I'm going to need to use the chain rule. Okay? So derivative of x squared with respect to y is 0. Derivative of 10xyz with respect to y, I'm going to need the product rule because I'm multiplying both y and z together. Now the 10x I'm treating as a constant. So I'll leave that outside, and I'll do the product rule on the y and the z that remain. Derivative of y with respect to y is 1 times the z unchanged. And now swap them. Now I leave the y unchanged, and now I multiply by the derivative of the z. Okay? Plus the derivative of y squared, that's going to be 2y. Plus the derivative of 8z squared. I need another chain rule there. Derivative using the power rule, I get 16z times the derivative of z with respect to y. On the right-hand side of the equation, derivative of 0 is just 0. Okay? Now I need to isolate partial derivative of z with respect to y. I'm going to start by multiplying in the 10x. So I get 10xz plus 10xy partial z partial y. And then I get the plus 2y and plus 16z partial y equals 0. Just as before, I want to isolate the terms with my derivative in it, with that partial z partial y. So I'm going to leave them on the left-hand side, and I'll move everything without that derivative to the right-hand side of the equation. So I'm left on the left-hand side with 10xy partial z partial y plus 16z partial y. And on the right-hand side, I get minus 10xz minus 2y. I can factor out the common partial z partial y, leaving me 10xy plus 16z. I didn't change the right-hand side at all. It stays the same. And now divide by 10xy plus 16z to isolate the partial z partial y. So I have found the partial derivative of z with respect to y. I'm interested in that partial derivative value at the point -1, -1, -1. Okay, so now plug in -1, -1, -1. And I get -10 times -1 times -1 minus 2 times -1 divided by 10 times -1 times -1 plus 16 times -1. This is a -10. This is a +2 divided by, this is a +10, and this is a -16. -10 plus 2 is -8. 10 minus 16 is -6. And I again get 4/3. That's how much the z changes per change in y. So if I change the y by 1 unit along this tangent line, then my z will change by 4/3 of a unit. And I'm not changing the x at all because I'm holding it fixed in this direction. Okay, and so I have my two tangent vectors. These are vectors tangent to the surface, which means they are parallel to the tangent plane. So if I just take the cross product of them, it will give me my vector that is normal to the tangent plane. So my normal vector is going to be 1, 0, 4/3 crossed with 0, 1, 4/3. Plug in the vectors, take the cross product. For the I component, I get 0 minus 4/3. For the j component, I get 4/3 minus 0, so it's 4/3. But then because it's a j component, it's negative, so -4/3. And for the k component, I get 1 minus 0, which is just 1. So there's my normal vector, -4/3, -4/3, 1. My tangent point, as you may remember, was -1, -1, -1. Put that information together, I can construct my tangent plane. First component for my normal vector, x minus the x component of the point. Second component from my normal vector, y minus the y component of the point in the plane. And finally, the z component of my tangent vector, and then z minus the z component of the tangent point. And so I get negative 4/3 x plus 1, negative 4/3 y plus 1, and z plus 1 equals 0. Okay? And that's fine as a final answer. If it's me, I'd actually multiply both sides of the equation by -3. That would change the first component into a positive. Mathematicians, we tend to like the first component to be positive, the first term to be positive, if we can help it. And it would also get rid of the fraction. So if I multiply both sides of the equation by -3, I'd get 4x plus 1 plus 4y plus 1 minus 3z plus 1 equals 0. It's the exact same equation, just written a little bit differently. So that is the equation of the plane tangent to this implicit surface at the point -1, -1, -1.